Good afternoon, everyone. This is Spencer Snolling from Hydromantis, and I'm glad that you can join us today for our regular webinar series. Today we're going to be talking about GPSX and how to use our analyzer function to do automatic sensitivity analysis. I was just talking to my colleague Rajiv earlier today saying I can't believe we've been doing these webinars now for over 6 years. So I'm glad that you could make it, and we enjoy bringing these to you and interacting with you in this sort of unique and interesting way and helping you to get the most out of your use of GPSX. So as I mentioned, today we're going to be talking about analyzing a wastewater treatment plant using the GPSX sensitivity analyzer tool. My name is Spencer Snolling. I'm VP of Product Development here at Hydromantis. And the agenda for today's webinar is really just to talk a little bit about sensitivity analysis first, and then to talk about the analyzer feature that is built into GPSX that allows you to do that in a very simple and straightforward way. We have several different kinds of sensitivity analysis that is available, so I'll run through those very briefly. Then we'll talk about, as we usually do, how you actually go about doing that in the software, how you set up sensitivity analysis, and then we get to the part that's always my favorite part, which is actually running demonstrations on my desktop, and we'll just do a couple of quick sensitivity analysis that you can play around with yourself. And of course, we always encourage you to ask any questions that you might have. If something pops up along the way, you can use your GoToWebinar dashboard in the questions panel. Just type that in there, and then I will stay around at the end of the webinar to answer any of those that you think of along the way. So first of all, what is sensitivity analysis? Well, sensitivity is really looking at how much does the output from my model change when I change my input. It's a way of measuring that sensitivity, that slope of the response for my model. And of course, it's a very generic thing, and we could be talking about any particular input and output. But usually the way that it's used in most analysis is looking at one of the important input parameters to the model, like the size of the tank or the influent load or what have you. And how, when I change that, how does my particular plant design change over time? So I want to know how much of an effect that change in my design is going to have on my effluent. So if I increase my tank size, is that going to improve my effluent quality? So the reason this is a useful thing is that you can really isolate what the effect of one particular variable on your overall plant design. And you want to be able to do that so that you can understand how that variable affects all of the other things that are going on in your model. Now, activated sludge is, as you know, a very complicated thing. So sometimes you find that certain parameters, your system might not be very sensitive at all to certain parameters and very sensitive to others. And you may find that it's even within a given parameter that it may be very sensitive in one part, like one range, and very not sensitive in another. And so doing sensitivity analysis on your design is a really excellent way to get a handle on exactly how the model is going to behave under different conditions. Now, you can, of course, do this manually. You can basically run your model, put it together, run some simulations, and then you can put the number in, run that, record the output, and then move that input again up a little bit, and then record the results and do that over again manually, stepping through a series of input values and recording all those results as you go. And that's what often we do. However, the GPSX sensitivity analyzer tool is designed specifically to be able to do that for you in a super efficient way. Basically, this is a tool that runs multiple simulations for you. It automatically adjusts the input to your model from one simulation to the next, and it collects all of the output from all of those simulations and then graphs that and plots it for you in a nice way. Generally, what you're looking for is essentially what is the output versus the input change, and we want to be able to see how that works. So this is part of the GPSX Pro license. If you're not sure what license you have of GPSX, most people have Pro, but if you are unsure what you have, just send us an email and we can sort that out for you. And it is there basically to save you time and effort and to do sort of rigorous data collection for you and put that all into one report. It provides you that easy method to see the relationships between plant loading or operation or design and the performance of that particular plant. So you'll be able to plot something that looks like this, where I'm looking at my effluent ammonia versus my influent flow. And as a matter of fact, this is the example that I'm going to do here for you shortly. So you can activate the sensitivity analyzer when you're in modeling, in simulation mode. Basically, there is this sensitivity analyzer button. It is actually a button and a drop-down menu kind of combined together. It's located right here. It's right next to the optimizer button, and I'll point you, if you want to know all about the optimizer, to another webinar that we just did several months ago about that. So the analyzer feature essentially is going to run simulations for you, move some input around, and then plot those results. Now, as I mentioned, we have several different types of sensitivity analysis. And so just to quickly run through what those are, we can first of all do a steady state analysis. So we're just going to change one variable and we're going to get a steady state solution for every stop on the way as we go from a low value up to a high value. And we're going to get a complete steady state solution for each one of those. We also have what we call our phase dynamic. Excuse me. This is essentially the same thing, except that after steady state has been completed, we then run a dynamic simulation and we collect the data from the end of the dynamic simulation. So if you had something where I want to change one particular variable, but I don't want to just get a steady state answer, I want to see what happens after it's been running for a few days or weeks or whatever, the analyzer feature will make the input change for you, solve for steady state, run a dynamic simulation to the end where you specified, collect that data point, and then make the change, do it again over and over and over again. And then we have time dynamic. Time dynamic is, again, for doing dynamic simulations, but in this case, we want to be able to plot several different runs together on the same graph. And these are all done doing step analysis. That means I specify a range of input that I want to go. So, for example, if I wanted to see what happens with my plant at different recycle rates, I pick a low rate and a high rate, and then a step, a delta, as you want to be able to move up from the low one to the high one. That'll dictate how many runs you're going to do. And then we also have, separately from that, a Monte Carlo analysis, which is a probabilistic way of doing sensitivity analysis where you specify a number of input parameters and their distributions. And then you can do steady state or dynamic analysis with the Monte Carlo feature as well. Okay, so coming back to talk about those a little bit in more detail, and we're going to run some demonstrations. Essentially, in the step analysis, we are going to pick what we want to happen across the bottom axis on this graph here, on this x-axis. Now, normally in GPSX, you're used to seeing time on this axis. However, now when you're running a sensitivity analysis, we want the variable of interest, the one that you're changing, that input, to be the independent variable. So you're going to specify, I want to run this simulation over and over again while I change the influent flow from 1,000 up to 3,000 meters cubed per day. That allows us to see a value of the model output at each one of those steps along the way. And we're solving for a steady state solution at each one of those steps. Now, a phase dynamic analysis looks very much the same. It's very much the same way of displaying information, except that it's not just a steady state solution. It's steady state plus a dynamic run of some number of days that you will have specified. And then we collect the data point from the end of that run and then plot that versus the influent, or pardon me, in this case, influent change, but whatever your input is, we plot it versus that. So in this particular case, I could say if I had some dynamics happening in my system, I'm going to run for 0.8 days. And what this is really a plot of is a steady state solution, plus we run it for 8 days, and then we collect the data after that. And then lastly, that time dynamic analysis. This is one that's really good for trying to see what is going on in a really short period of time where something changes really drastically. And in this particular case here, we can see this is effluent ammonia numbers at different influent flow rates. And we can plot a bunch of these together. You can specify how many you want And each one of these is a different solution to the model. So we could have an influent flow here, and then we can step that up, and it plots the dynamic simulation. Again, this is now showing time, the thing that you're normally used to seeing. If you want to be able to see the individual dynamics of what's happening in your model, and you want to see that align for every one of the runs that you're doing, then this is the way that you would set this up. So in that drop-down menu that is next to the sensitivity mode button, this is where you would select these things, and I'll show you that here in a moment. Okay, so how do I set up a sensitivity analysis? Well, the first thing you do is you put together your regular model just as you would at any time, and you select the scenario, and you basically get to the point where you want to run your scenario, run your system. Then you choose whatever input parameter and make sure that you've added it up there on the input control tab. So usually when you drag it up there, it will appear as a slider first. By default. And now what you want to do is switch it from slider to analyze step. I'm going to leave out the Monte Carlo discussion for a little bit later. Right now we're going to switch it to analyze step. That means that I'm going to run this particular model, and I'm going to start from the minimum value that we're going to specify up to that maximum value, and there's that delta. It tells me that I'm going to run this in steps of 100 meters cubed in this particular example, starting at 1,000, going up to 3,000 in increments of 1,000. So it's going to make 20 runs in this particular case. So once that is done and you close that menu, you'll notice now that that thing no longer looks like a slider. It's now red. That indicates that this is a tool, a parameter that is going to be adjusted by our sensitivity analyzer tool. You select which type of analysis that you want to run here: steady state, phase dynamic, time dynamic, those ones that I just described. And if you're using a dynamic one, then you need to also specify the amount of time that you want to run. So set the stop time. That's basically the same as you would do in any normal dynamic simulation. And then hit run, and then it'll start up the whole thing. And you'll notice that it runs one after another immediately. You don't have to do anything in terms of collecting the data. All of that will be collected for you and spit out for you in a report at the end. Okay, so let's take a look at what that would look like. So I made a super easy, simple example of how this would work and how you could use it to analyze an existing wastewater treatment plant. So in this particular example, this is a very small plant. This is only 250,000 gallons a day, so this is sort of almost pilot scale type plant. So in this particular plant, we want to understand for its size and its operation, what is the maximum loading that we can accept to the plant while it's still continuously nitrifying and doing the job that it's supposed to do. So let's move over here to simulation mode, and we can see here that if I were to, let's just look at some effluent first of all. If I run this plant, just let it go to steady state, we can see that for this particular flow rate coming into the plant, that it is fully nitrifying. Our effluent ammonia is 0.7, so it's doing the job that it's supposed to do. All of that ammonia has been converted to nitrate, and it's doing what it's designed to do. So now, how much can we increase that influent flow and still manage to continue to nitrify? Now, again, I'm increasing the actual flow rate here. I'm keeping everything else exactly the same. All the influent concentrations are the same. All of the details of the operation, we're keeping the wastage the same, and all of the other things. There are ways that you can tie a lot of those things together so that you could increase things sort of together in a way, but just for simplicity's sake, I'm keeping everything exactly the same. And now I'm going to run that again. Okay, so it was at 0.7 before, now we're at 0.8, and I can beef this up a little bit more, and now we can notice we're up at 0.1 and a little higher. And we can see now when we get into this range here around 1650 that we're starting to lose nitrification. If I move it way up here, we can see here now ammonia is 25, so we're not nitrifying at all, and there's no nitrate. So this is telling us, of course, now that we've exceeded the capacity of this plant to fully nitrify. Now, if I were to move way down here, of course, it'll go back to where it was previously. So that gives us kind of a feel for what the behavior of the plant is at all of these different loadings, just by running it around. As I mentioned, you could sort of do that manually by just doing that on your own, recording, changing input and recording and so on. Now, this is where the analyzer tool comes in handy. I can come up here. No, pardon me. First of all, I need to change the slider over to an analyze control. So I can right-click here, input control properties, and this is where I'm going to set which of these parameters I want to change. So here's influent flow. I'm going to go to analyze step, and you'll notice this becomes available for me to adjust. And what this is saying is we're going to run a number of simulations where the influent flow starts at 500 meters cubed per day, goes up to 5,000, and we're doing it in steps of 100 meters cubed per day. So now this switches. You can see that's red. And now we turn on the analyzer. Turn on analyze mode. I'm going to do this just for steady state. You can see down here in the bottom right corner, it's telling us what we're doing. And I am going to now show you this graph. So this is effluent quality, and we can see here effluent ammonia nitrate. And we can see instead of time on this axis, we're now looking at influent flow because that is the parameter that is the analyze. The analyzer is going to switch for us. Okay, so I hit start, and now it's running consecutive steady state solutions, and it plots all of that information for us on the graph. And we can see here that, of course, at the low end, so this is ammonia is in black here. At the low end, at the lower loadings, of course, we are able to nitrify with this particular given plant. And we can see very clearly identify that point at which we've now started to exceed the ability of this thing to fully nitrify, and suddenly our ammonia goes up and our nitrate goes down. And that's a fairly clearly a breakthrough that we can identify here at around 1,800 meters cubed per day. So this is a nice way to do that kind of analysis, is to be able to set a low point and a high point and then run a number of simulations, get all those results back, and be able to look at that nice and cleanly for this particular relationship. Now you could, of course, go back and try this again. It's all sensitive to whatever the parameters are that you've set. The ones that you're not making part of your sensitivity analysis are still playing a role here. So you'll get a different answer here if I waste differently or if I do it at a different temperature and so on. So I plotted other things here too as well, and whatever graphs you make, they will all be filled out as part of this sensitivity analysis. Here we're looking at effluent COD and BOD. We can see here that of course there's a breakthrough there as well when the plant loses its ability to continue to treat. For BOD, it's actually a much higher breakthrough point at 2,600 versus what was this again, 1,800. So that makes intuitive sense. So we can now get an understanding of how this particular plant is sensitive to changes in loading. So in a way, what we've done here is capacity analysis. We've identified where that capacity is for this particular plant. Now we could switch it around. I'm going to do this just for illustrative purposes. We could do this, switch this around the other way, and instead of changing the load, we're going to keep the load the same. Let's look at what will happen at different temperatures. So I'm going to switch over to the other variable up here, and we're going to run at temperatures of 5 degrees Celsius up to 25. And now what I need to do actually is to reset this model so that it will now sort of redraw this graph now for liquid temperature. And so we can now see that we're going to run a sensitivity analysis with liquid temperature. We're going to go from 5 degrees to 25, keeping the loading the same. All right, so now when we run this, we'll see here that the plant at very cold temperatures down here, this is like 10, 9, 8, 7 degrees Celsius. Those are very cold temperatures there. It's not nitrifying. But once we get up here to about 13 degrees Celsius, so that's the low 60s Fahrenheit, this is, actually I can even change that unit there. Let's make it in Fahrenheit. So here 55 degrees suddenly gets to the point where it can suddenly start nitrifying. And so our ammonia goes down and our nitrate goes up. So now this is, of course, as I mentioned, still just for the loading that we're working at. If I change this here to, let's go up to a much higher loading and redo that, we're going to get a different graph. We'll see now that, it's not quite as robust. The shape of the curve is different, and so we could play around with all these different analyses here to understand where that point is that it's going to be able to continue, or at least to start nitrifying there at cold temperatures. Okay, so that's the kind of thing you can do. You can certainly put any other parameter that you want. Anything that is an input into GPSX can go up on this graph and up on this table, and you can set the sensitivity analyzer for it, and then you can plot whatever you want. It will literally plot anything versus anything that you want to be able to put up there. And so it allows a very interesting relationship to be drawn. Sometimes you see exactly what you were expecting to see. Sometimes, and that's of course the really great part, is when you see, oh, that's interesting. I wonder why that is, and then you get to play around with it in different ways to understand how that relationship is built in your system. Okay, I'm going to come back to my slides again. I'm going to only briefly touch on Monte Carlo analysis because it is a whole different thing unto itself. It is sensitivity analysis in the sense that we are running large numbers of simulations with different inputs. However, it's done in a very probabilistic way. And I would like to do a whole separate webinar just on doing Monte Carlo analysis in the future. So we'll just mention here that it's set up almost exactly the same way that you ran the thing that you were just looking at, but instead of stepping from a low value at a consistent increment all the way up to the high value, you instead specify a distribution of inputs. So for each parameter, for like example here, we have autotrophic maximum specific growth rate. We specify that there's a mean and a standard deviation, and so we're going to run a large number of simulations where we randomly sample from this distribution, and then we get a solution for the model each time, and then we plot the distribution of outputs. So GPSX allows you to specify which shape of input that you want for each of the parameters, and you can specify the mean and standard deviation and the other things for the other distributions, and then you collect all the outputs. So we have a nice example on this that comes part of the sample layouts menu, and you can see there's a design of a plant. And again, we're plotting effluent ammonia. We run it for a large number of simulations, and we can see here that, well, 50% of the time it's going to fall below 10 milligrams per liter. So that's obviously, we don't want it to be failing 50% of the time. So as you start to increase the size of that plant, you'll notice that it starts pushing more bars here to the left, because basically you're changing the distribution of the output now. We're making more of the particular simulations, a larger fraction of them, fully nitrifying. So it's a very interesting methodology. It's a bit of a brute force one because it requires you in Monte Carlo analysis to run large numbers of simulations to be able to fully define what the distribution looks like. And it's a common tool that's used in uncertainty analysis. And as I mentioned, I'm going to come back and do a whole webinar on that someday. So for the sensitivity analysis tool as it stands in GPSX, the typical things that I see people using it for, and the ones that I use it for myself, are capacity analysis, taking a plant and then increasing the load. Sometimes we do the flow, sometimes we do the concentration, sometimes we customize things and do both at the same time. We have operational analysis, looking at effluent quality versus internal recycle versus anoxic zone fractions, and sometimes you can pull a bunch of those things together, looking at SRT, mixed liquor versus the amount that you're wasting, and even getting into looking at the other operational parameters and their effect on the overall cost of running your plant. And as you know, in GPSX, we do some analysis of the operating cost in terms of energy requirements and so on, and all of that information can be included in your sensitivity analysis. So it's a very handy tool. It's basically doing something you could do on your own, but that would be very time consuming and tedious. So therefore, we built this automated tool that just runs things over and over and over and collects moves the input for you and collects all of the output, saves you time and effort, and it provides a lot of flexibility with those different types of simulations that you can do.